This is 2.2, dealing with higher degree polynomials. We've moved on from 2.1, where we learned how to do quadratics with coming up with equations given a graph or graphing given an equation. We're going to expand upon that idea now and be looking at what we call higher degree polynomials, but the concepts that we learned with quadratics still are going to move on and grow as we deal with these higher degree polynomials. So our objectives here are to grow your knowledge of standard form and factored form. Like I said, we had dealing with that when we were looking at quadratics. We're going to deal with that still. We're going to relate factors, x-intercepts, roots, solutions, and zeros. We're going to determine key features of graphs, which are of the higher degrees, and then determine a process for linking a graph to an equation. So you don't have to write this down because you already did when we were dealing with quadratics, but again, what I need you to know is in your book, you're going to oftentimes hear them refer to zeros or roots or solutions, and when they're asking you to find a zero, root, or a solution, they're just trying to find the x-value of an x-intercept. The reason why we love these is because it directs us to that factored form. Those zeros, roots, and solutions are just the x-values of an x-intercept, and they help us with the factors. If you know your roots, you know your factors. If you know your factors, you know your roots. Very important. We could use, given a graph, that knowledge of our x-intercepts and put it into an equation. Very, very important skill. And then, of course, you also have x-intercepts. These are all very much interlinked. Alright, also one thing is, I don't want you to forget about bouncers. If you ever do try to find the x-intercepts of factored form like this, well, you could go ahead and rewrite this as x plus 4 times x plus 4. And now here's the deal. When you set this equal to 0, this function equal to 0, because you're trying to figure out where does this cross the x-axis, so where the y value is 0, what's going to happen is you set the same darn thing equal to 0 and solve for the same darn thing. So in other words, you have an x-intercept at x equals negative 4 and x equals negative 4. Right? This is what we call duplicity of solutions. If it ever asks you for the duplicity, it's just saying that, hey, you could have the one solution or the one x-intercept, but it's happening in what we would call 2 times. So if it asks you for what are the x-intercepts and its duplicity, I would just say the x-intercept, or the solution, I should say, is negative 4. The x-intercept would be negative 4, 0, but it happens 2 times at that particular place. Oh, and remember that these are bouncers, so when we looked at the graph, this is a positive graph. So we are going to have that x-intercept right here, and it's going to do that bouncing, right? That bouncing character, because it was a squared root or it had a duplicity of 2. If you ever have a cubic, so this would be setting x minus 1 equal to 0 3 times. So what you could just say is that x equals 1, x equals 1, x equals 1, or you could just say x equals 1 and the duplicity is 3. Okay, so duplicity is 3. Now what this looks like, the shape looks something like this, where here's 1, and it's going to kind of look like a bouncer. We do know what cubics look like. Go over 1, up 1 for that parent shape, go back 1, down 1 for that parent shape, and it does something like this. Parabola down, parabola up. Whoops, I missed my mark. But the idea is, it kind of acts like it's going to bounce, but then it does that weird squiggly parent shape through that point of duplicity, 3 times duplicity. So that's the behavior of a cubed factor. Okay, so like we had a character for the squared factor, we have a character for a cubed factor. We have bouncers, and then we have that squiggly character. Alright, so what's going to happen now as we move on to 2.2 is we're still going to use the same concepts of how you graph quadratics. You might want to find those x-intercepts, and then we find what we call that vertex, and then that helps us graph. Those x-intercepts are very, very key. Same thing when we move into these higher degree polynomials, those x-intercepts are absolutely key. So here is, as we discovered in our intro activity to these higher degree polynomials, here's our factored form. And for as many factors as you have, that's how many x-intercepts you have, even if there's some duplicity there. And here's standard form. So one important thing is the degree of a polynomial. We're going to find that the degree of a polynomial, it's the highest exponent value. A degree 3 polynomial would have the highest exponent value of 3. So it would look something maybe like this: 3x to the third minus 2x plus 1. This would be an example of a degree 3 polynomial. This also, I could maybe have it out of order, so 1 plus 10x minus 2x to the third. So this also is a degree 3 polynomial because you're going to look at each one of your terms. And again, terms are just pieces separated by addition or subtraction here. So here's our 1, 2, 3 terms here, and I suppose I'm going to throw on a plus x cubed or x squared. So here, I mean, you have 4 terms. Alright, but it's a degree 3 because the exponent, the highest thing was 3. If I had put a 4 here, then this would be a degree 4 polynomial. Here's an important thing to capture. A degree 2 polynomial is going to have 2 factors. Okay, so very important to note. A degree 3 polynomial could have 3 factors. Okay, so knowing that it has 2 factors or 3 factors here, we also know it has 2 solutions. Alright, a degree 3 polynomial with 3 factors. If you know your factors, you know your roots. We have 3 roots or solutions as well. Alright, same thing, degree 4 polynomial. We call degree 3 polynomials cubics, degree 2 polynomials quadratics. These two have special names. Anything beyond a degree 3 is just called a degree 4 polynomial, degree 5 polynomial, degree however many factors or solutions it has, it's just a degree n polynomial. Okay? So here's an example. It's number 33. What we are to do is find all the real zeros of this polynomial. So the first thing that we're going to want to probably do is get this into factored form, because that's going to help us find those zeros. If you know your factors, you know your zeros, or in other words, your roots. So here I'm going to notice that each term, I'm going to change this to plus and negative. Each one of these terms are separated by these addition signs, and what I can do is note that there's a 3x in each one of them. So what I'm going to do is I'm going to divide everything by 3x so that I can multiply everything by 3x. So I'm going to just take these piece by piece. I have 3x, and then 3x cubed divided by 3x to the first. That's going to just be x to the third minus 1 because we're going to reduce that exponent. So we're going to get x to the second. Here we're going to divide negative 12x to the second divided by 3x to the first. So we're going to have minus 4x plus, and then 3x divided by 3x would just be 1. Alright, so here's the start of the factoring. Now we're looking at a quadratic and we're thinking, alright, how can we factor this quadratic? This one's a little bit trickier. If you try to, you're going to find that you can't find any factors of 1 that add to be negative 4. So what we'll have to use is the quadratic formula. The quadratic formula will also give us solutions of a quadratic. So here we go with x equals negative b, so positive 4, since we're going to look at negative 4, plus minus square root b squared, so negative 4 squared would get us 16, minus 4ac all over 2a. Okay, because this would just be 1. Alright, so x equals, and then 4 plus minus the square root. When we simplify underneath the radical, we get 12 all over 2. And then now, leave no perfect square underneath the radical. What we would have is 4 plus minus, and then 4 times 3. I'm going to note that 4 is a perfect square and a factor of 12. So haven't changed anything at all, but now what we can do is break that radical. So we have x equals 4 plus minus 2 square root's 3 all over 2. So here we have x equals, this 2 can divide everything, so we're going to have 2 plus minus the square root of 3. So what we have, find the real zeros, set this factor equal to 0, 3x equals 0, and then divide by 3, x equals 0 is one of our roots. We set x squared minus 4x plus 1 equal to 0, and use the quadratic formula to solve that. So what we have is x equals 2 plus the square root of 3, and x equals 2 minus the square root of 3. So here we have all of our zeros. Alright, the leading term This is a very important vocab word as well. The leading term is going to be the term with the highest degree or exponent for its variable part. So what is the leading term? I am going to change this to plus and negative here. Plus and negative because polynomials are terms separated by addition. So we're going to look through, and this is not in standard form because normally standard form starts with the highest degree, but this one right here is going to be the highest degree that we have. So this is called our leading term. Negative 2x to the fourth is our leading term. This is important to be able to identify because that degree and that exponent of that leading term is going to tell us a lot about our function. So first of all, like we were mentioning, the exponent tells us how many roots or solutions or zeros we should look out for. This is what we call the rational root theorem. The number of solutions is based on that degree. So like in this problem, what we can do is we can expect there to be 4 roots. Alright, so 4 roots should be what's expected. The exponent is also very important because it tells us about our function and whether it's even or odd. So first, what we would want to look at is we have what we call end behaviors, and the end behaviors are just the directions that the y take off in. So this is what we're going to say, does y approach, is it going up or is it going down? So is it going up or is it going down? And we're going to use infinity as an indicator of up or down as x approaches to the left. So as we go in the negative direction, what is the y doing? Is it going up or is it going down? Okay, so negative infinity would be the left end behavior as x approaches negative infinity. The right end behavior is going to be the direction that y takes off as x approaches the right, or in other words, as we're going towards the positive infinity in the x values, are we going up or are we going down with the y values? So I'll bring all this together in a second, but the even functions, the highest degree is even. So in this case, what we can expect is the end behaviors will be the same. Alright, so for example, this is an even function because it's a degree 4. Degree 4. So what we know is this is a function where either both end behaviors will be going up, there might be some curvature in here, but both end behaviors will be going up or both end behaviors will be going down. Odd functions is going to be when the highest degree, when we're looking at that leading term, is that exponent even or odd. If it's odd, it's going to be an odd function. The end behaviors will be doing the opposite of each other. So this one, our leading term is negative 3x to the third. So this is an odd function because the degree is 3 and 3 is odd. So now it's either going to look something like this or it's going to look something like this, where our end behaviors are going opposite directions versus the same. So here's kind of just a visual to remember. Even-tempered functions and behaviors point the same. They're either both going negative infinity or both going positive infinity. So even-tempered functions, hey, you know what they are. They're either always happy or they're always sad. He's totally happy, he's even-tempered. He's totally happy, he's totally sad. Odd-tempered. Is it happy? Is it sad? We can't really tell. They're kind of odd. We don't know. So this one, they're going opposite directions. Alright, so the sign of the leading term is also important because it's going to say if it's a negative or if it's a positive type of function. So this is going to be a little confusing at first, but even functions with a negative exponent, even we know that they're both going the same, both same direction as we're approaching the left and the right. So if it's negative, what we're going to know is as x approaches infinity, so as we're going to the right, as x is going towards the positive direction, y is going to approach negative infinity. So this one right here is going to be that situation, that as we're going towards positive infinity, we are going down because it's negative. Alright, so it's going to go down. This is another way of saying down, but this is how we're going to want to write it. As x approaches negative infinity, so as we're going to the left with our x values, what is y doing? Well, it's also going down. Okay, they're going the same direction. Okay, so even function, it's a sad, totally sad face because it's a negative. Alright, so even, we still know that they're going in the same direction, so this one would be even and negative. We could expect the coefficient, the leading coefficient, to be negative, and that the leading term has an even degree or exponent. As x approaches infinity, y is approaching, now this is going to change, we're going to go towards the positive with the y values and the positive with the y values as it's going towards the negative. So these two would be example of even positive. Another way to write this is instead we could say as x is approaching infinity, y approaches infinity. That's another way to write a shortcut with these approaches. Just use these arrows. And what we're saying is x is going towards the right, y is going up. That's all we're saying with this notation. Alright, odd functions, they're going to be going in the opposite directions. So whatever you say for the right end behavior, as we're going to the right, what's going to be for the left end behavior would have to be opposite. So these will have to be different. Okay, so as x approaches infinity, this is a negative. Ultimately, what we're going to end up is sad. Okay, so he's an opposite, odd, and he is negative because ultimately he ends up sad. Okay, odd-tempered, can't really tell, but he is ultimately sad. So here we are saying as x approaches infinity, y approaches negative infinity, alright? And then as x approaches negative infinity, y approaches infinity, alright? Because as we're going backwards towards the left, y is going up. What about this one? Is this one odd? Yes. Is this one negative? No, because ultimately in the end we're going up. Okay, so this one's going to be a positive coefficient. These are still going to have to be opposite of each other, but you'll see that it's going to be this one that switches. So we're going to ultimately end up happy. So this one is a positive guy. Still kind of odd, can't really tell. Same thing here.
So here's an example. Now that we know all of what we know with that leading term and what it tells us, we're going to have to determine the right and left end behaviors of this function right here. So first of all, I'm going to highlight that this negative 5x to the third, that is our leading term. So what that tells us is we have a degree 3, so this is an odd function, right? And it's negative, so it's going to be a negative odd function. So I can tell you that, this is a little messy because I lost my pen here, but as x approaches, and then we're going to go ahead and say the positive values. Because this is negative, ultimately the y is going to be going down, or in other words, going towards negative infinity. So this right here is my right end behavior. And then the other end behavior would be as x approaches negative infinity, so in other words, as we're going towards the left, what is y doing? Well, y is going to be going in the opposite direction of this. It's going to be going up. Okay, so this is my left end behavior. This is your homework. What I am going to go ahead and do is do a couple more problems. So I had that intro assignment where you had to graph these higher degree polynomials. And now, knowing all the information that we know with our end behaviors, with what these leading terms tell us, we can know a little bit more about our functions. So, for example, number 4, we have to match it up to a graph. So, knowing that this is a degree 3 polynomial, I have 1, 2, 3 roots. I should expect 3 roots. Another thing that I know is my end behaviors. Because this is positive, this is a positive odd function, I know to look for the one with 3 x-intercepts that is going to be having end behaviors where ultimately it's going to be going up, and then it's going to have end behaviors going in opposite directions. When you look at all the different ones there, this is the graph that's going to stick out to us because we have 1, 2, 3 roots to match our degree 3 polynomial, and it's a positive odd, so we can see that, yeah, as x is going towards the negative infinity, we're going down, but ultimately as we're going towards the positive, it's going up because it was positive. They're going different directions because it was odd. All right, number 7, same thing here. You could go ahead and factor this one. There's an x cubed in both of these, so I could go and write this as x plus 2. because I'm dividing everything by x cubed. Oops, sorry. Alright, so here is that. So we have a triple or a duplicity root at x equals 0. So this is going to be x equals 0, and there's going to be 3 times of that, and then x equals -2. So when you look at all those different graphs that you have to match up to, these are the roots that you should be looking for. So I'm just going to show you. Here we have a -2 and then a 0, and there is that cubic character. Because we had a duplicate root 3 times at x equals 0, it did that squiggly through it. If you were in any doubt past that point, you could always plot some points, kind of check it out, see what this graph looks like. But otherwise, we also know that the end behaviors, it's a positive, right? Positive, and it's even. So they're going to be both pointing up in the same direction. As x approaches infinity, y is also approaching infinity. As x approaches -infinity, y is also approaching infinity because it's even and positive. Good luck!